So this video is about a tutorial related to the transformers. So this is we'll solve a problem related to the transformers, and in this problem I will cover about how we can draw the equivalent circuit, and also get the parameters of equivalent circuit and Phasor diagram. So I will keep this area here only for putting in the important values. And if you see the values of the transformer, the question given, this is the question which I have formulated. So the data could not be accurate practically to a transformer. So the values taken here are more theoretical. So this is not accurate to practically a transformer, but it is a theoretical problem which we are solving here. So it can be a little wrong, or there could be some mismatch when we are comparing with an actual transformer, but the problems given in exam could be very much the same kind, or it could have some kind of things which you will want to take into consideration. So the question here is a voltage of the transformer at the secondary side is 1000, and the current drawn at the secondary side is 100, and the power factor of the current at the secondary side is 0.8, which is lagging, and the other parameters is magnetizing current drawn, or the no load current drawn is 1 ampere, and it is 30-degree leading. So, and the resistance of the secondary side is 0.08 ohm, while the leakage reactance is equal to 0.25 ohm, while for the primary side the resistance is 25 ohm, while the leakage reactance is equal to 150 ohm. So, and the number of turns, or the turns ratio, N is equal to N1 by N2 is equal to 10, and so that's all. So now its first thing is how to draw the equivalent circuit. Considering the basic parameters can be drawn, so the equivalent circuit of this transformer could be drawn something like this. So the question is to find out V2, V1, E1 and I1 currents. So, and also draw the phasor diagram from this if possible. So this is how I can draw my equivalent circuit for the transformer. And so this is what is my V1 voltage, and this is what is my V2 voltage, and this is my R1 resistance, and this is my X1 reactance, this is my R2 resistance, and this is my X2 resistance. This is my RC, this is my core loss component, and this is my magnetizing component, and this is my I0 current which will come from here, and this is my I1 current which will flow from here, and this is my I2 dash current, and this is my R2 dash and X2 dash when I am taking it to the other side. So what is my R2 dash is equal to my R2 into a square, which is equal to 0.08 into 10, which is equal to 8. And similarly my x2, if I compute, it will be equal to 150 or 0.25 into 10, which is equal to 25. And those are the two important components. Now we have to find the other components like I2 dash. To find out the current I1, the I0 current is given. So this was the first step. This could be, if this is not asked in the question, there is no need to solve for this. And the second part is, so what we have found out, I am just writing here, R2 dash is equal to 8 ohm and X2 dash is equal to 25 ohm. Now my impedance Z2 will be equal to, can be written as 0.08 plus J 0.25, and my current I2 can be given from the power factor, which was 0.8 lagging, which will give me a phi angle of close to 36 degree, which will give me a cos phi plus J sin phi is equal to and considering my current I2 is 100, so resolving it in terms of the complex, so we will use complex numbers to solve this problem. So you'll need to have some idea. Into 100, so this into 100 will give me what is my I2 considering the power factor. Writing my current in terms of the power factor, so it is 100 into 0.8 minus J 0.6, so my I2 is equal to 80 minus J 60. So if I say that this is my third equation and this was my second equation, this was my third equation, then it is possible to get E2 as equal to what is my V2 plus, that is this, plus whatever is my current here. So my I2 dash will be or whatever is my I2 dash, that is what is my load current here, so that is equal to I2. So again my I2 into what is my impedance of Z2, so this is equal to 1000 was my secondary voltage, so this plus of I2 is 80 minus J60 into my Z2 is 0.08 plus J of 0.25. So this will equate close to, if you will solve this, then I have already solved this, and this will come up to 991.4 plus J 15.8. If you are resolving it in complex numbers in polar coordinates, it will come up to 991.4 or 991.12 with an angle of 0.91 degree. So this is your E2. So what you have got is your E2, which is equal to 991.12 which is making an angle of 0.91 degree with the y-axis. And again, if you are, the next step is finding the E1. So my E1 is equal to AE2. So this is my E1, which is here, which I will get here, is equal to AE2. So if I'm multiplying the transformation ratio, which is equal to N or equal to A, so whichever way notation you are using. So if you're multiplying it by 991.4 plus J 15.8, what you will get is the value of E1, which if you are solving, you will get it close to 9914 plus J 158. If you are resolving this in polar coordinates, you will get 9915, making an angle of 269 degree with the x-axis. That is, if you are starting here, this will be your E1 will be lying somewhere, which is making an angle of, so it will be lying somewhere here in this case, which is making an angle of 269 degree. So your V1 will probably be lying somewhere here. So this was your E1, and your E2 would be lying somewhere like this. So anyway, if you're, so that's all about solving. So what you have got is your E1, which is 9915 with making 269 degrees. So if I'm rubbing this whole thing, so the next point is finding my I2 dash. So I2 dash is equal to I2 divided by 10. So this was your load current, which is I2, and whatever current you are getting here is your I2 dash. So I2 dash is equal to I2 divided by 10, which is your I2 is your I2 is equal to 80 or I2, whatever you have found out was 80 minus J60, and your I2 dash will be minus of this. So there will be a change of sign, since this is to draw your phasor diagram, and we are considering that if you are having a phasor diagram like this, your I2 will be in this direction while your I2 dash will be in this direction. So there you'll have to take the minus sign here, and so it will become, if you solve it, if you're dividing this by 10, you will get 8 minus 8 plus J 6. So again your I0, which is equal to what is given is I0 is given in the question, and it is equal to 1 ampere, and is making 30 degree lagging. So it will be, if you are solving it, it will become 1, and the I1 will be making a angle of 30 degree with the x-axis, and if you are considering it, the angle of the I0 with what is your E2, then it will be something like 0.91 plus 90 plus 30. So your I1 will be equal to 1 divided by 1, making 190 120 degrees. So your why you need to consider your E2 here is because you are going to solve this to get your I1. So again, if you are solving this, it will come up to something like 0.51 plus j of 0.857. So your I0, what you have found out is 0.51 plus j of 0.857, and now if you are finding the value of I1, it will be close to what is minus 8. My I1 will be my what is my I2 dash, which I found was minus 8 plus j6. So my I1 will be my I2 dash plus I0. So it is minus 8 plus j6 plus my I0 is close to 0.51 plus 0.857. So when I am computing this, I will find my I1 close to having a value of minus 9.2 plus j 9.91, which is equal to having a value of 13.5 is to 138 degree in polar coordinates. So this is my I1 is equal to 13.5 making 138 degrees, and the value of I1 is equal to 9.2 plus j 9.91. And the next step is finding my value of V1. So my value of V1 is will be equal to minus E1 plus I1 Z1. So this is minus because it is this EMF induced is opposite to the supply voltage. So you'll have to take the minus sign and plus the leakage reactance here if you are applying the KCL to this loop. So this will be plus minus sign, and here it will be plus minus sign. So you are applying KCL to this loop. This way what you will be getting is this equation, or KVL, sorry. So if you are solving that, the full equation can be written as 9914 plus J158, which is a value of, or minus sign here, which is a value of E1, and plus minus 9.2 plus J 9.91 into 25 plus J150. So this is equal to which comes up to 11630, or minus 11630 minus J1785. So this comes close to 11766, making an angle of 188.72 degree. So this was what was my V1 was all about. So V1 is equal to 11766, making an angle of 188.72 degree. So you have found out your V1 in this, which is equal to 11766, you already knew your V2, which was equal to 1000 volts, and you also found your E1, which is equal to 9915 volts. So also the I0, which is already given, was 1 ampere. So based on this, all the values have been found out. Now it's possible to draw a phasor diagram of this. So this is how the first step was computing the values, and now you can draw the equivalent circuit. Also it's possible to draw the phasor diagram. So I'll just draw. Next step after finding out all the values is drawing the phasor diagram. So I have drawn the phasor diagram here, and I will just show. And there was an error, which was a mathematical calculation error in the calculation, which was the value of E1 which was computed was having an angle of 180 degree, unlike the 269 degree which was found out. So that was an error. So just correcting that. So what we found out is, we found that, so this is how I have drawing this phasor diagram. So it's possible to draw it by considering 0 degree from the x-axis, or it's possible to consider it by it's possible to draw it by considering 0 degree from the y-axis. But while drawing from the y-axis, considering 0 degree starting from the y-axis, one advantage is that it gives a quicker symmetry of having better symmetry of having the values like E1 and E2 exactly opposite each other, so that you can quickly have an idea of how they stand. So this is my 0 degree which I am starting from, or my reference point is y-axis in this case while I am drawing the phasor diagram. Again, this, when I am coming to the x-axis, this is my 90 degree and this is my 270 degree, and when I will come back here, this will be my 360 degrees. So what all values which I have computed was, it was given that the power factor was 0.8 lagging, and the I0 was given as 30 degree leading. So this was what was my I0, which I can show in the graph, having a value of 1, and it is having a 30 degree angle. And if you are considering it, if you are trying to compute it from the reference which we found out, was it was having an angle of close to, so that's what was I0. And then what we found out was, we found out the value of E2. So the value of E2 was found out to be 991.12, and it was close to 0.91 degrees. So this is 0 degrees, then my 0.91 degree will be something very close to the y-axis. So I have shown it in the y-axis itself as the value E2. And then what I found was the value of I1, and before going to I1, the value of V2 is given as 500, and this is making an angle of, if I am considering this as a value of V2, then it is found that the current I2 is making a value of 5 with V2. So this phi angle is 36.6 degrees. So I have drawn I2 here, and then after the I2 I have drawn V2 here at 36 degrees from the V2. And then the next was the I2 could be extended as I2 dash here, and the I2 dash was found like minus I2 dash is equal to minus 8 plus J6. And what we found out for the value of, for finding out the value I1, we found I1 as equal to 13.5 and making 138 degrees. So from here it is, my I1 is 138 degrees from here. That is a reference which I am taking. So I can draw the I1, just 13.5, and if I am projecting I2 to my I2 dash to and I'm adding the I naught here, then it should add up to what my I1 is all about. So I1 is equal to I1 is equal to I naught plus I2. Then I found out my E1, which was equal to 9915. So and it was close to 180 degrees. So 180 degree from here is my E1. And then I found out my V1 was 1176, and this made angle of 188 degrees. So 188 degrees from here. So this is where my V1 will be. And if you are adding the values of I1 R1, which is I1 vector is this one, and if I am adding it to with both the component for the resistive loss and the component I1 X1 for the reactive loss, then it will add up to what is a V1. So you can show both the loss component here, and this will be making angle of 188 degree. So this is again making a perfect kind of phasor diagram. And again, while drawing the phasor diagram, it's very much possible to know if there is some error, like one of the computational errors which I was having, which I just found out. So again, it might be quite something to wonder why my V2 is here. This is something which I have drawn here is something which is wrong. One of the main reasons why this is wrong is that while I have taken the reference to be y-axis, so that's one way to take the reference is the y-axis, but the reference you have to take is taking the reference considering V2. So I will just have to erase this. So my V2, it will not make any difference in this case, because my V2 will be, if I am drawing it, it will be something very close to this way. It will be somewhere very close to this way, so that the angle in this case, this angle will be 5, which is a power factor. This is V2, and this is my E2 vector. If I am drawing as per scale, it could be larger or smaller. So this angle 5, which I found out, was 0.91 degree, which is close to 1 degree. It's approximately, which can be said that my E2 and V2 will both lie on the y-axis. So in that case, it was possible to take the y as a reference. Otherwise, if there is a large difference, like angle difference, which is usually if it is 10 degrees, then you will have to consider that this V2 as your reference if the secondary voltage is given. So it's possible to take the V2 as a reference, and since the angle 5, which you will find the power factor will be always considered against the I2. So that's one way to start how drawing the phasor diagram. And in this case, if whatever angles which you are finding, you will be finding with reference to or with respect to the V2. So that's again, that was the case in which we had found out our angle of I naught, which was close to 120 degrees, and this 120 degrees was with respect to V2. So when you are considering this 120 degrees with respect to V2, so the 30 degree which leading was given was with respect to the x-axis. So again, when you are finding it with respect to the V2, so that was the reason why we had taken the value of, we had computed the value of I naught as being equal to 1 into 0.91 plus 90 plus 30, which had come up to close to 120.91 degrees. So that was the reason why we had taken that, and again it will make no difference, because if you are considering it with the x-axis, whatever was given, it was 30 degrees. So again, it will make no difference because if you are considering it with the x-axis, whatever was given, it was 30 degrees. So but at the same time, while you are drawing the other values with respect to, so it was necessary to convert the value of the I1 in terms of how it was seen with respect to V2, or with respect to the voltage as a secondary side. So that was the reason, if you'd have wondered why this was changed here. And it was possible to draw the value of I0 somewhere here from the secondary side, how it would have seen, and that would have added up to the graph in a perfect way when you are finding the value of the I1 and everything else. So this is how you can represent all the values in the phasor diagram. So this is more for giving a quick overview of how it can be better used to understand the problems taught for the engineering graduates, etc., which could be helpful in solving the problems given in the textbook, etc. So this problem was not from a practical transformer, but it was more theoretical, and this was just computed by me while I took random values. So most of the thing have ended up being seemingly correct, but when you're comparing it with the practical values, it might not be very much accurate.